starting with a binomial distribution and using a normal distribution as an approximation. At the end of the last video we looked at this example where we had to use a suitable approximation to calculate this probability from this binomial distribution. We looked at using the formula from the formula book, and the highlighted part gave a math error on the calculator. We looked at using the inbuilt binomial probability distribution on the calculator, but that's an exact binomial distribution and not using an approximation, so we can't use that method either. So we looked at using the normal distribution as an approximation, and we said that if we calculate the probability that y is equal to 140, the problem with a continuous distribution is that when you have equals in your question, you're not shading anything. You only shade something on a normal distribution if it says less than or more than or between values. But equals, you don't shade anything, and the area shaded is the probability, so the answer is 0. So we need a workaround when using approximations, and the workaround is only specific for approximations. Any question that starts off as a normal distribution question, the answer to something like this will be 0. But if you start off with a binomial distribution and you're using an approximation like we are doing here, then we would use something like this, which is called a continuity correction. And all I've done here is I've started with 140, gone half a unit down and a half a unit above. Values in this interval round to 140, and because we have an interval, that would be an area shaded on a normal distribution sketch, so we have a probability that's not 0 this time. So here's the actual graph, and px equals 140 is here. What I'm going to do is take this portion of the graph and just enlarge it and exaggerate it a little bit to have a look at some of the properties. So the red line here represents the binomial probability for x equals 140. So we have 139 and 141, and with the 140 I'm going half a unit down, half a unit above. The shaded area is represented by this probability, 139.5 to 140.5. So this is the probability that the calculator's built-in statistical functions gave for the exact binomial distribution. And now I'm doing this calculation for the normal approximation. So I've put in the lower and upper limits, 139.5, 140.5. The standard deviation is the square root of the variance. The mean is 150, and we have this probability. And if you compare them, they are very similar, but they're not exactly the same, because this is, after all, an approximation, but a very good approximation, because our n value was really large and p was exactly 0.5. So far we've seen that if we start with a discrete distribution, for example the binomial, and to calculate probability we go from the binomial towards a continuous distribution, the normal distribution in this case, we have to make modifications using half a unit. So something like this, px equals 10 in the binomial distribution. So equals 10 means we only want this value. Now if you look at the boundary between what you want and what you don't want, so I want the 10, I don't want the 9, I don't want the 11. The boundary here and here, in between the 9 and the 10 you've got 9.5, there it is. In between the 10 and the 11 you've got 10.5, there it is. That's another way of looking at where these two values come from. So in this example, binomial probability, we want less than or equal to 7. So we actually want all of these, 0, 1, 2, 3, 4, 5, 6, 7. And I'm using an example here where n in the binomial distribution, the number of trials is 80, which is why you'll keep seeing 80 in my numbers here. So once again, the boundary between what we want and what we don't want is right here. And between 7 and 8 we have 7.5, and that's where this comes from. We were doing less than or equal to in the normal distribution. If you put an equal sign here, it's not going to change anything. You can if you want to. I haven't. Okay, next one. Greater than or equal to 15. So we want these probabilities. and the boundary between what we want and what we don't want is right here. It's between the 14 and the 15, so that's 14.5 there. We were doing more than or equal to on this side, we're doing more than on this side. Again, if you did this or this, it's not going to change anything. Okay, next one. Here we're looking at the probability that x is between 4 and 8 inclusive. It's not just between 4 and 8, it's between 4 and 8 inclusive. It includes the 4 and it includes the 8. So we want these probabilities. And again, we don't want this region, we don't want this region. So here's one of the boundaries between what we want and what we don't want. And there's a second boundary on this side again. So we have between 3 and 4 we've got 3.5, there it is. Between 8 and 9 we've got 8.5, again there's the value. And you'll notice all of my binomial probabilities all have equals in them. Greater than or equal to, less than or equal to. So what would you do if you had a question like this, px less than 8? Well, first of all, rewrite it with the equal sign. Less than 8 in a binomial distribution means less than or equal to 7. Then continue with this method. If you had greater than 14 means greater than or equal to 15. So then you write this and then you continue with this method. And likewise, if you had between 3 and 9, I'm not using the word inclusive this time. Okay, so between 3 and 9 will be these values, 4, 5, 6, 7, 8. So then you just continue with this method. So this diagram summarizes the basic principles behind the approximation. We look for these conditions to make sure that the approximation is valid, and if these conditions are met, then we look for the continuity correction, we work out our mean and variance, and then we continue as we would normally do in the normal distribution to calculate probability. And you would do this in any question that starts off as binomial and you see the words estimate the probability or using a suitable approximation work out the probability.